Okay, in this video, we are going to be talking about prime factorizations of whole numbers. But first, we're going to introduce the fundamental theorem of arithmetic, which is a theorem that is proven and is foundational to our work with prime numbers and prime factorizations. So it says every whole number greater than 1 is either a prime number, so its only factors are 1 and itself, or it's a composite number, so not prime and not 1, that can be represented as a unique product of prime numbers. So here's an example. 45 is a composite number, and its prime factorization is 3 times 3 times 5. So what we see there is that 3 and 5 are the multiplicative building blocks of 45. There's no other way to factor down 45 into prime numbers. Like every prime factorization of a number is unique to that number. Let's see an illustration of this. So this prompts us to make 3 different factor trees for 360, showing that they all end in the same prime factorization. So no matter what pathway we take, pulling apart 360 by way of a factor tree, which we will see 3 examples of here, no matter what journey we take, we're going to end up with the same prime factorization of 360, no matter what. It's unique. There's only one way to factor 360 down into all primes multiplied by each other. All right, so let's get started. Let's see here. So here, to make a factor tree, we just think of 2 numbers that multiply together to make 36. Or I was thinking about 36 to make 360. I am going to choose 36 and 10 because those are right there in my brain. Like I know that 36 times 10 is 360. Now I see if I have any prime numbers here. Nope, they're both composite. They can be factored further. So I just keep going until I get down to all prime numbers. And 36, I could have factored this differently, right? It could be 18 and 2, or like I have 9 and 4, or 6 and 6. And no matter what journey you take, you're going to end up in the same place. So you can factor however you like. Okay, I have one prime factor here. So I'm going to stop and highlight that. Actually, I have 2. 5 is also prime. Okay, but over here, I need to keep going a little bit longer. I have 3 and 3. Those are both prime, so I'm good there. And then 2 and 2. Okay, I'm going to highlight all the ends of my tree branches that are the prime numbers. And I'm going to write down that 360 is equal to, I like to put my primes in order from least to greatest, but it's not mandatory. You can put them in any order you want. So 2, how many 2s do I have? 1, 2, 3 times 2 times 2 times, and I have 2 3s, 3 times 3 times, and just 1 5. So the prime factorization of 360 that I found through my factor tree is 2 times 2 times 2 times 3 times 3 times 5. Now, I'm going to take a different pathway for my next factor tree of 360, and I should end up with the exact same prime factorization. Let's see if it happens. We sure hope it does. 360, 360, well, I could just cut it in half. I know that 180, I happen to know from like thinking about degrees, 180 times 2 is 360. I've already got one prime. I've got a long way to go with this one. Let's see. I could cut that in half again. 2 and 90. Just thinking about my degrees for my angle measures. These are familiar numbers from that. Okay. And, oh, that wasn't paying attention and I did too many much highlights. Okay, so 2 is prime. 90 is not. Why not pull out another 2 and do 2 and 45? 2 is prime. 45 is not. What is 45? 45 is 3 times 15, I think. 15, 30, 45. I've got another prime. And I think I'm going to get down to all my primes here. 15 is 3 times 5. Okay, so I should have ended up with 3 2s, 2 3s, and a 5. Did I? 1, 2, 3 2s, 2 3s, and a 5. I did, even though my journey was very, very different. All right, let's really drive this point home. We're going to make one more factor tree for 360, and we're going to end up with the exact same prime factorization, I'm hoping. Okay, so 360, why don't I do like 360? Why don't I pull out a 5? Okay, I think I need my calculator for that one. That's okay to use your calculator sometimes. That's 72. Cool. 5 times 72 is 360. Okay, 72. Do I know two things that multiply 72? I think I do. 8 and 9. Oh, and I can highlight my 5 because that is prime. Okay, 9 is 3 and 3. Those are highlightable. Those are prime numbers. And 8 is made up of 2 and 4. We got one more prime there. And 2 and 2 makes 4. All right. Did I end up in the exact same place? I probably did. I hope I did. Not liking how that highlights looking, but I think it's all right. Okay. I have 1, 2, 3 2s, 2 3s, and a 5. And that's it. So you can see these factor trees look very, very different from one another, but we always end up with the exact same prime factorization for 360 because it is unique, according to the fundamental theorem of arithmetic. All right, let's look at one other thing that we can do with prime factorizations. So here we have the fact that 60 is equal to 2 times 2 times 3 times 5. I want that up here. 2 times 2 times 3 times 5. That's the unique prime factorization of 60. Show how to find all the factors of 60. So we can take, actually, I just want this. So we can take the prime factorization and recreate all of the factors of 60, not just the prime ones. So we have been finding the factors of 60 previously by, say, making rectangles out of 60 squares and finding the dimensions of those rectangles, or we've been using trial division with calculators, but we can actually build the factors out of these prime number building blocks. So here's how we can do that. First of all, we want to start with 1 and 60. I'll just make a little list. We want to have the number 1 always as a factor, and then 60, which we would get if we multiplied all 4 of these together. It's just so easy to forget 1 and the number itself, so I always like to start with those. Your personal choice where you can start. And then I'm going to take all the possible versions where it's just one factor. So I know that 2 is a factor. I don't need to repeat 2 because I already have it on my list. 3 is a factor and 5 is a factor. Now I'm going to start taking pairs of factors, like all possible combinations of pairs. And I don't need to repeat ones. So is that going to give me all my pairs? Let's see. So 2 times 2 is 4. 2 times 3 is 6. 2 times 5 is 10. And then I don't need to do 2 and 3 and 2 and 5 because I already did them. And then 3 times 5 is 15. So that's all the possible pairs of factors multiplied together. So here I'm generating all the factors of 60. Okay, and then I'm going to erase up here so I can think about next up, I'm going to make combinations of triples. So I could do, let's see, 2 and 2 and 3. Let's start there. 2 times 2 times 3. 2 times 2 is 4, times 3 is 12. I could do 2 and 2 and 5. 2 times 2 is still 4, times 5 is 20. Okay. I could do 2, 3. I could do 2, 3, and 5. 2 times 3 is 6, times 5 is 30. Then, are there any other triplets that I could do that would give me new numbers? I've done 2, 2, 3, I've done 2, 2, 5, I've done 2, 3, 5. I think that's it, yeah. And then all four of them together, that was 60. So I think this is my complete list of factors. Now I could rewrite these if I wanted to in numerical order, least to greatest, because as you can see, they aren't necessarily going to be in order from least to greatest, the way that we've generated them. But we could also put them into factor pair order. Like I can see that we have 1 and 60, and then 2 and 30 would be paired together, 3 and 20, and then 5 and 12. Mhm. And then 15 and 4 and 6 and 10. So we have factor pairs. We could reorder it according to factor pairs or from least to greatest, or we could just leave it as this list because we don't always have to put it in order of least to greatest if that's not asked for or necessary by the question. Okay, so that is our final example, and that is all.